this time let's take a look at moving average process. To motivate this model, consider real SMP return, small rt, which is simply computed as log difference of annual SMP index. Usually the annual stock return in the US and Korea and other countries as well displays no serial correlation. So it appears to be quite random. Okay? Now suppose you compute what is called holding period return, where using this notation at time t, you are adding two of them. Okay. The one returned at t and previous period. Okay. Of course, you can construct rt plus 1, 2, where you're adding rt plus 1 and rt. Right? So you can do that. Right? So you have 1 year return sequence as original data. Okay? You are computing this two holding period return in this way. For instance, in eViews, you can use this function called move sum. So you calculate moving sum. So if original return is denoted by CCRT, continuous compounded return, and then input, the first element is the data, this one, and the second one is the period. Okay. Then the sequence, this one, is going to be two holding period return. Okay. Obviously, two period return will be serially correlated, RT, t plus 1, and so on and so forth. Why? Because there is a overlapping terms. Right? Overlapping terms. So, although the original annual return has no serial correlation whatsoever, the way we construct this holding period return, the new series will exhibit serial correlation. So here is the example. If you calculate this one is for 2-year holding period return and its autocorrelation function. So do you see that? Serial correlation is non-zero. Okay. So if you calculate 10-year holding period return, then each holding period return have 9 observations in common. Right? So stronger serial correlation. Right? Okay. So if you look at the simplest moving average model, which is the first order moving average process, it can be represented in this way. But as you can see, in a previous example, two period return, this could be RT, this could be RT minus 1, and theta 1 is minus 1. Right? Minus 1. That makes two period return, right? So very similar. So even though ET exhibits no serial correlation, X of t will be serially correlated because of this structure. Okay? Similarly, we can represent this MA1 process using lag operator, or in short notation, theta of L, which is the polynomial in lag operator L. Okay? Simulate AR1 process. This is a particular example. As you can see, it's bouncing back quite often, right? Compared to autoregressive process, which moves kind of slowly like this. The reason being, if we interpret E of t as shock to the system or news to the system, the memory of this shock to the value of x, well, one period and contemporaneous period. So the moving average process of order 1 have memory, just one period, and then this dissipates. So if there is a shock, 1 unit shock in this quantity at t minus 1, it won't be affecting xt plus 1. So current shock will affect this one. Previous shock will affect this one, but not the other shocks, right? And we know that if you recall AR1 process, on the other hand, AR1 process, previously if it is stationary, one of the examples was like let's ignore mu, just for simplicity. We could rewrite AR1 process in this form, right? But here, contemporaneous shock will affect the current value. Previous shock will affect the current value, and all of them. So the memory structure between MA1 and AR1, which one is longer? AR1, right? Just short-lived memory, just one period in this case. In this case, more distant paths affect current value, but because we know that for stationarity, this condition has to be met, the magnitude of this one will diminish quite quickly, exponentially actually, right? So, well, if this holds for t and rest of them, it should hold for t plus 1, t minus 1 as well, right? Because it's stationary time series. So shifting the origin shouldn't matter, right? So if you calculate, let's say, using our calculus notation, what is the partial derivative of this guy? Shock at t minus 2 on t. Of course, pi 2, right? But this is same as dxt plus 2 det. Because stationarity, right? So if you plot this quantity on a vertical axis, and 1 period, 2 period, and 3 period, and so on. So if you calculate those numbers this way, we call it impulse response. So this is a response. 1 unit change in E of t will affect the value of x at t plus 2 by that much. So impulse and response. So impulse response function. Okay. So obviously, impulse response function for AR process is going to be exponentially declining, whereas MA1 it is short-lived. We also learned that partial autocorrelation of AR1 process will cut off after lag 1. Right? But for MA process, it's the other way around. Here, for MA1 process, partial autocorrelation cuts off after lag 1 and 0. And this is partial autocorrelation function. It dies off. So exactly the opposite. Okay. If you have Q lags, then of course that's MAQ process. So autocorrelation function will cut off after lag Q and then and then 0, right? So that case. And quick question. Suppose theta 1, the value of theta 1 is 1. So if you calculate the root of this part, let's say theta 1 is 1. Is xt stationary? In an AR1 process, if this is 1, it is not stationary, right? If this one is 1, which is the root of this AR1 process lies on unicycle, right? It has to be outside unicycle. So this has to be the case. So what happens if pi 1 is 1? Well, non-stationary, right? Very similar structure here. What if the root is 1? Is that series stationary? The answer is very simple. It is stationary. The reason being, let's say, suppose theta 1 is 1. What is the expected value? 0, right? 0. What is the variance? Well, the variance of E of t, sigma squared, and then this constant is squared, so plus theta 1 squared sigma squared, which is constant. So variance is constant. Covariance, how to calculate covariance at lag 1? Well, you take a lag on both sides. So xt minus 1, t minus 1, t minus 2. Okay? In e-views, if you have a data, then simply you can type v squared data, including mean of the process, and MA1 to MAQ. This is only one confusing part in e-views is this is more or less universal notation. So this polynomial theta has same structure as pi polynomial in our process. So this is kind of mirror image. But in e-views, it will return not this theta 1, negative of theta. So this value. So take note of this slight difference of convention used in e-views. So in EBIUS, it reports these parameters. Okay. You can easily see that, well, the moving average model should provide you the parameter estimate as you expected. See? We started with the previous 2-year holding period return case. Single period return was simply the sum of small constant and disturbance time, random error. Now we are creating 2-period return. So this is your data, X. Okay. Suppose you estimate this model using this. What you expect is MA1 process with this coefficient unit 2. Right? Unit 2. See? ET plus 1, ET minus 1. Okay. So expect this one is 1. This one is 1. So let EBIUS estimate using 2-period return as a dependent variable and constant. This is theta 1 coefficient, which turns out to be 0.979. Very close to 1. So you find correct parameter. That should be very close to being 1. We can practice that later. So let's continue. Thing called mixed process here. Mixed process is the one that has both autoregressive part and the moving average part. By introducing both autoregressive part and MA part, you can achieve more conveniently the principle of this. You don't have to write very lengthy MA model or very lengthy AR model. So if you build model in this way, called this process, then perhaps you could model particular data as where you have 2 legs of this and a single leg of this instead of ARP process, very lengthy. Notation, we have both AR part and MA part. If you have long-term mean, mu, then we can estimate this one by simply typing least square x of t c, which is this one, and then AR1, AR2, and MA1, MA2, MA3. And there you estimate this number, not intercept. So previously, I illustrated the difference between this model and the one without considering long-term average, where you can learn the least square of x of t and c and this one. So xt minus 1, xt minus 2. If you do that, then in that case, constant is going to be just intercept time, not this long-term average. Now here is simulated P is set equal to 1 and Q is set equal to 1. And you need a little bit of exercise, so you can actually show that the ARMA1 process will have 0 expectation in this setup. There is no constant appeared here. So you have 0 long-term value. And you have a feature like this one, so like moving around this mean. And also this feature, which makes things bumpy. But if you actually look at ACF and PACF, it shows, obviously, it shows tapering off feature. Although slow, it shows some tapering off feature, and it shows cutoff feature. But this time, 1 and 2 partial correlation appears to be significant. So what makes things a little complicated here is like this one. Previously, we learned that if it is purely AR process or is purely moving average process, then there is a kind of cutoff feature in PACF or ACF, depending upon whether it is AR or MA. Right? But when you have both of them, then the pattern of these two functions is not obvious anymore. It depends upon the magnitude of I and beta. The reason why these two are significant is not because there are two parameters in this problem. It's accidentally turned out in that way. Well, think of it, but if you don't have that part, obviously then there's only one significant one, and then the rest of them 0, and the taper off, right? So basically, if you're actually interested in moving from pure AR or MA process to mixed process, the significance of this or reading off these two functions, sample functions, won't be giving you direct information about what should be sort of optimal to P and Q, those lags. So we'll talk about other procedure if it is suspected to be coming from some mixed process. So that's going to be discussed here. Here. So before we do that, this one, some of you may have learned the subject of regression analysis from statistics or econometrics. Okay. Well, basically the estimation of this type of model is very similar to those methods, actually the same one. So we are not getting into the detail about how we derive a parameter estimate using those techniques, but let me briefly touch on what we are doing there. So in your typical application, you've probably done, for instance, simple regression, y on x. Okay? So here is x, here is your y. So if there are data, then finding straight line is of course least square, right? If you actually calculating, let's say, curve, that's not linear, right? So something that's not linear is non-linear. So non-linear model could be looking more like, let's say, function of alpha, beta, and gamma given data x, t, and this. So this is a linear function, this line. Okay? But this function f could be anything, right? Square root curve, this one, or something exponential, right? Or even having more structure than that. But the way these least square and nonlinear least squares are constructed is given, let's say, some guess value on parameter, O parameter, you have a data x and y, right? Or x and xt minus 1. So given your guess on parameters, you can calculate this one, right? So if you calculate this given parameter, let's say its hat is computed residual, it could be positive or negative, right? So you square it to make it positive or positive. And then sum it over from your observation 1 through, let's say, cap t, all observations. Okay. This particular value, we say sum of squared residuals, that is computed for particular value, right? Your initial guess. So you want to find the value of parameters that minimize this quantity. The smaller this one, that means you have tighter relationship. Right? So actually, if you choose the wrong alpha and beta, so if you draw a line like this one, then residual is very big. E of t is very big. If you find right one and E of t is very small, right? So changing this number means you are moving this thing, right? Back and forth. So you can find something that minimizes the whole thing. That will give you this line. Okay? So even if your problem looks more like this, and finding this curve, the same thing. Residual can be computed, right? So you can minimize this. And there is a well-known result in the literature saying that if your sample size is big enough, the estimated value from non-linear least square is in fact the same as the one from what is known as maximum likelihood estimation. The reason why we use least square estimation, if problem is well defined situation is a little complicated, but suppose that's not problem. So usual situation, if you apply least square estimation to obtain parameters, that parameter estimate have very nice, desirable features like something called blue, best linear unbiased estimator, whatever it is. There is a good color, only one good color in this least square estimation, blue. But if you apply this method, because things not linear, so even if it's non-linear, still the estimate you get from this one has very nice or desirable property. Okay. So in E-views, you are actually applying this one, where when thing is becoming straighter, then it will become straight line, right? So linear case is included in the non-linear, the general non-linear case, right? So in E-views, this one is default. Okay. The reason is, you see, think about how to calculate E of t in this problem. Well, E of t is obviously calculated as the difference between xt and this quantity. What is Et plus 1? Well, t plus 1 and t. So if you have x data, you can calculate this sequence and square it, sum it over, and try to minimize it, right? But suppose you have this situation. Well, what is Et? This minus that minus that. Then what is Et minus 1? We don't know. Right? So actually, the expression for moving average process, including moving average part, this function, sum of squared function, the autoregressive process, this function is linear in parameters. In this case, pi 1. This sum of squared function is well-defined function, so you can find the minimum quite easily. But if you have moving average term, then this one is very complicated term, which is the nonlinear function of parameters of interest. So we require this one. So obviously one way to define E of t is, let's say if you don't know what is E0, for instance, if you are at t equals to 1, then you need to know value t is at 0, right? If you don't know the value, actual value, then why not assume central average or unconditional mean, which is 0. So you can assume E of 0 is 0, and then you can recursively construct E of t. So if you start from there, then E of t is some function of previous values of this one, which makes nonlinear in theta 1. So even if you are assuming E of 0 is 0, still the error, margin of error, could be trivial, very small, negligible. Because we know that basically E is assumed to be centered around 0 with constant variance sigma squared. So it won't be that bad initial guess. So if your sample is big enough, then the influence of this assumption will be very negligible, trivial. Now the maximum likelihood estimation is slightly different. The maximum likelihood estimation, you can apply that to this problem, or this problem, or this problem, or even more complicated problem, where you need to make some assumption about this to calculate likelihood. For instance, let's say T is distributed normal with mean 0 sigma squared. Our previous assumption is, of course, assuming these two moments only, without referring to any distribution assumption. Right? But if you have to apply maximum likelihood estimation, then you need to make an assumption. So if normal assumption is reasonable, then it's okay. We'll get to this MLE later on. You know, when we try to handle a little more complicated time series model, maximum likelihood estimation is very nice one and very powerful one. So we'll get to that part later. Okay. Now, diagnostic checking. So we know that for stationary process in ARMA modeling, if you happen to know P and Q, then you can apply nonlinear least square and find those values in no time. Okay? But how to determine P and Q? That's one question. Suppose true data generating process for X is P equals to 1 and Q equals to 1. 1, 1, like this one. Okay. And suppose you estimated, let's say mistakenly, 1, 0 model. So if truth is this, then this is obviously misspecified, right? Because we are treating this one as one big E of t, right? So if you estimate X of t, which is generated from 1, 1 process, mistakenly by 1, 0 process, then residual will exhibit serial correlation, right? Serial correlation. It's like moving average term, creating, you know, even though E of t sequence is independent observation, this moving average term will create serial correlation. So this is one way to check whether the model is reasonable. Okay? So if you tried this, then probably you will see serial correlation, and we talked about Q statistics last time, right? So if you find serial correlation, then you can decide, well, there is something more to be modeled, to be included in your model. Okay? So your next move could be, why not try P equals to 2 and this one is 0. And then get the residual and see if there is any serial correlation using Q statistics. You may find additional serial correlation there, even if you estimate this model, or serial correlation may disappear. Okay? So you can keep trying these combinations. Of course, you can also try those models as well, right? But actually, AIC, SCBC, those are things called information criterion. It is a concept like this one. Probably simple regression you probably understand better. Suppose y and x are expressed in this way. So suppose this is the case. Okay. Suppose you additionally included z of t, which is redundant variable, any variable, and you include it as a second regressor. What happened? If this is true, and you accidentally included redundant variable in your regression, if things go well, then the coefficient to this one will turn out to be 0. Right? If this is true. Right? But if you actually try that, then the coefficient, let's say gamma, this will be numerically non-zero, 0.001 something. Not exactly 0.0. Right? Well, what is the consequence? Well, because this number is going to be measured or estimated very small, so even if you included it here, when you try to relate this one, when you change z, y won't be changing much. So nothing much being hurt, right? So it won't hurt much, even if you throw in some extraneous variable in your regression. Okay? If you keep adding other variables, very similar, those coefficients will be statistically insignificant small numbers. Right? On the other hand, the t statistics of this one will start decreasing a little by little. So we say, well, standard deviation of estimated beta, standard deviation of estimated alpha, if you correctly estimate this model, then this has a very nice feature predicted by the thing called the best linear unbiased estimator property of least square estimate. So you can't get any smaller variance than that if you apply least square as an estimator. Okay? But if you add more and more, only downside is this number is going to be slightly increasing. So we say you are losing efficiency. It won't make your estimate for alpha and beta biased. There's no bias. It's okay. But this one is going to be slightly increased. So it becomes less efficient. So when you get rid of those, then you get best estimate, unbiased one, and the smallest standard deviation. So largest t-value. Right? When you do this type of exercise, adding redundant regressors in your model, if you keep observing what happened to R squared, coefficient of this determination, whether you throw in some sensible variable or just nonsense variable, if you add explanatory variables to your regression, R squared will keep rising bit by bit. Okay? That's a technical aspect of least square. Okay? But as I said, if you add more and more of this, the accuracy of this will decline, right? So instead of calculating that, we say well, R bar squared. So we try to penalize the increase in the fit, goodness of fit, by possibility of adding some irrelevant parameters in your model. So that's this version. Okay? So the similar thing happens. If you keep increasing P and Q, the goodness of fit in terms of this one will increase. Whereas the precision of those parameter estimates will decline. So there is a trade-off, right? So we'll use that trade-off in this type of statistic, of course, this t statistic refers to t statistic of this one. If you try to judge whether a particular p-q combination is good or not, you obviously look at significance of individual coefficient estimates, as well as goodness of fit, particularly in terms of R bar squared. Also, you will check Q statistics of residual, but still it won't give you the answer. Well, what P and Q appears to be the best? That one will give you an answer. These three will give you an answer. So before we get to that part, let's take a look at the example one more time. Here, invertible process. And by invertible process, what I meant was absolute value of this one is less than 1, right? If it is invertible, previously we know that for this 2P return, theta 1 estimate was like 0.97 or something, very close to being 1. So still, the absolute value is less than 1, so it's invertible, right? So this is MA1 process, having root very close to 1. So using the same data, suppose you estimated AR process, AR1 to all the way to AR5. We have those significant coefficients. Okay? Because this is the invertible process. So we know that if MA1 process is invertible, we can rewrite it as infinite order autoregressive process. So theoretically, if you keep adding those, it will all be significant. But at some lag, the significance will be very trivial. So after some lag, you won't be finding no more statistically significant. But still, the data appears to be generated from MA1 process, but we have more than one parameters in significant. So we have to decide whether we stick to there or MA1 process for the best fitting model. Then you, as I said, you check these t statistics and check the residuals, Q statistics, as well as adjusted R squared, 0.43. What's our adjusted R squared? 0.43 here. Previously, adjusted R squared 0.50. This one is greater. There's only one parameter to be estimated. This one is greater. So which one is better if you compare these two? Looks like this one better. Although it has small number of parameters. Okay. So how to choose between or among competing models? We use information criterion. Our objective is to achieve this goal. So first one, a Kaike information criterion is computed as this one. So let me explain what are notations. P is the order of ARP process. So if you first estimated AR1 model to see if it is best fitting model, So P is set to 1. Okay? And then you run a regression and you get the residual, and you can calculate residual variance. So the way this Akaike information criterion is constructed or suggested by Akaike is that calculate residual variance, take natural log, and T is the sample size of the regression, of course effect 1, and P is in this case 1, right? So you estimate AR 1. And 2 is the weight. So if you calculate, let's say, AIC for P equals 2, what's going to happen if you compare that result to those of AR1 model is AR2 process will lead you smaller value for sigma squared. Very similar to this phenomenon. Because AR1 and AR2, if you compare these two, AR2 has more parameters or more explanatory variables, right? X1, T, T1, T minus 1, and XT minus 2, second one, right? So it's like R squared is increasing, or the standard deviation or the variance of residual term will decrease. So goodness of fit will improve. So this number will decline if you keep increasing P. Whereas you are increasing this number, right? P. So if P increase, this will rise and this will fall. So two terms are moving to the opposite direction. So you want to find best fitting model that leading to some reasonable value, sigma squared, but this is, you can regard this one as a penalty term. You're overfitting. There is possibility of overfitting your model. By overfitting, what I mean is adding or including more irrelevant or redundant explanatory variables. So penalty term is this, and this is coefficient to this penalty term P. If you're familiar with log likelihood function, the similar effect could be found from calculating log likelihood under your parameter estimate, say from ARP P model, and take multiply minus 2, and the second term is the same. So if you are comparing, let's say, AR1 and AR2, so by fitting AR1, you can calculate this function. Fit AR2 process, also you can calculate AIC2. Compare these two and pick which one. According to Akaike, choose P that yields smaller AIC. Smaller AIC. So you will see that the example later. Well, because we've said that, let's go back to this one. Let's see it here. Akaike information criterion for this case was minus 0.46. Minus 0.46. How about the previous one? Minus 0.659. Which one is smaller? So there is no match between AR5 process for 2-period return compared to MA1 model. If two are competing, this is a winner. Also, in our lecture notes, there is a expression for Schwartz criterion, which has slightly different coefficient attached to penalty term. And BIC, that information criterion is not imported by eBooks, but some other software returns big. And actually, there are more than 3 information criterion you can apply. So which one you choose is okay. You can pick any one of them, but you need to know how to use it. Right? So what you do is you want to pick which combination is the best or optimal. I try, let's say, 1, 0, 0, 1, 1, 1, and so on. You can keep trying those combinations. Each time you write AIC or Schwartz criterion, okay? And try to pick that yields smallest value, right? That's your answer. So in this way, you don't have to worry about reading off the shape of sample correlation function or partial correlation function, right? When you have both of these. Of course, in this example, we have different value for P, but if you have ARMA PQ model, it's still same. Instead of P, you can have P plus Q. P plus Q. So if you are checking this model, instead of P there, you use 1 plus 2. Because you have 3 parameters to be estimated, right? In this case. This one stays, sample size stays, and ARMA 2-1 model calculate this one and get the natural one. Do you see the difference between these two definitions? So here, P works as a penalty. So if you include more parameters to be estimated in your estimation, that value increase. But how fast? So that's the weight, right? The type information criterion, the coefficient to the penalty term is 2, constant number. Schwartz criterion is natural of sample size. So if T increases, really increase. This is what I said. We fit this model and take this one, and number of parameters are P plus Q. Okay, so when you are asked to use a forecasting model, univariate time series model, the first thing I mentioned was to bring to a computer program, check it visually, and see whether it is stationary or not. So if it is non-stationary, you need to do something extra step. But if it looks stationary, then you move directly to this one. So first one is to see whether it is P or MAQ by examining sample statistic, sample correlation, and partial correlation. And then if it is purely AR or MA process, then the residual will be very clean, bottom noise sequence. Right? But because of our preference to simpler structured model, then very complicated model, well, we introduce a mixed process where both parts are included. Right? But here, PQ, we can't simply determine by looking at or reading off partial correlation function or correlation function. So, Darwin-Watson. No, we're not into well, the Darwin-Watson statistic is the case where, in a simple regression, for instance, here, look at this one. Of course, this E of t could be serially correlated. Darwin-Watson statistic is checking this case. But if you are estimating actually this one, suppose ARMA1 model is correct one, but you mistakenly estimated AR1 process, then obviously there will be a structure like this one, right? Like this one, right? Okay. So if you interpret this as that, this as that, then there will be zero correlation like this one. And I said we usually check that the presence of zero correlation using Q statistics with time series analysis, where in usual econometrics or statistic textbook, they refer to Darwin-Watson statistic to see if whether there is a positive zero correlation if rho is positive, or there's a negative zero correlation if rho is negative within some range. So in our output, it shows Darwin-Watson statistic, but usually it's for fun because eViews can handle this one in the same platform, because running a regression of this one and that, or this one and that, is structurally the same thing. eViews doesn't distinguish it, right? So eViews report this one from even this equation, but you can actually check Q statistic for this one from other menu after running a regression. Okay. Let's go back to this simple model. Well, even simpler. Suppose your exercise from examining or comparing those information criterion, suppose you end up with AR1 process is the best fitting model for your problem. And suppose you estimate this. Okay? Now we try to talk about how to calculate forecast. Well, suppose you are at time cap t, the last observation you have. So you are interested in, at t, what is the value? Next period. So cap t plus 1. So use notation like this one. This is your forecast. How to generate this forecast? And suppose x data looks like this. And this is time period t, t plus 1. What is your forecast? Well, I could say this is my forecast. How do I get it? Well, I just did it. Just arbitrary forecast. Because it looks good. Or better than just pointing this way. But, well, is there any better way of doing this? The clue is still this one. Well, we don't know, right? We don't know until actually we look more closely to this one. But before we look at this structure, like this AR1 process, we have to think about what is the criterion of judging forecast A is better than forecast B. In one sense, it is better, right? So there are many ways. Even my wife can give me some value as a forecast. My wife doesn't know time series analysis, but if I ask her to generate a forecast, she can just say, well, this number. Why? Because I feel like it. There are many competing estimates, right? Also, it could be forecast from this model, or it could be from ARMA 2-1 process, right? Or 0-1 process. There could be many competing models that can generate forecasts. So we need to set some criteria. So one of the criteria in statistics we use quite often is to think about mean squared error. Mean squared error. Mean squared error. What is mean squared? Well, as name indicates. Suppose this is your forecast, and suppose this is actual. So one step ahead forecast, right? So this is what? Forecast error. Right? Suppose you are at t+1. Actually, you can do the same thing, right? You can forecast and compare it with actual. Right? So suppose you repeated that procedure. So you are collecting those one period forecast error. Right? It could be either positive or negative, right? Depending upon your forecast, right? So you square it. Squared error. This is squared prediction error. So in Ender's book, it said mean SPE. So squared forecast error or prediction error, that is the average of that. So if you calculate this difference, forecast error, square them all, and then calculate the average, that's your mean squared error. So there will be one single pass for actual, right? But people make different forecasts depending upon their model. Right? So which one is more likely to better model? That yields smaller mean squared error. Okay. Suppose data is generated by this type of model, ARMA process. What is the best model? Well, what is model that produce minimum mean squared error? Minimum mean squared error. So model A will produce mean squared error. Model B, alternative model, will produce mean squared error, and so on, right? Which one will produce the smallest? If that is our criterion for judging which model is better, well, this is the way you calculate forecast for this one. What is t plus 1? This one, right? And it's rewriting, leading one period, right? Not lagging. So what is the expectation? But the one that gives you this desired property is to calculate this. Which is conditional expectation. Conditional expectation. Condition known at t. Known at t. So you are interested in this one. So notationally, this is the same. At cat t, if I write it this way, t, suppose t is the last time. So one period ahead, conditional expectation. So it's just one page long proof to see that, in fact, if you calculate conditional expectation, that forecast will give you the smallest mean squared error among competing models. So, what is the answer to this question then? AR1 process is simple. At t, this quantity is known, right? At t, we are interested in what is the value at t plus 1. So information up to t is known, right? So what is the conditional expectation using information known up to t, the time of prediction? This is known, right? How about this one? Not known. 0. I don't know. Right? So the answer is very simple. What is the conditional expectation of that? You can plug in. You can rewrite this one as t plus 2, t plus 1, right? Now, because t plus 1 is not known, you can use this one as proxy. Right? So you can continue to calculate this number. Only thing you need to worry about is what is your information. So something that is not known, then you can plug back in. So if this number turns out to be, let's say, 0.75, the forecast is going to be whatever it was times 0.75, which is smaller, right? So that way and that way. And eventually, you converge to this long average. That's the way this is calculated. In general, if it is ARMA PQ process where P and Q are fairly large, computation is going to be messy, right? But still you can do it, right? Before we get to that exercise, I'll do it next time, first thing in the lecture. If you want to calculate k period ahead, k step ahead forecast at time t, what you do is you calculate conditional expectation conditional on information of the cat t. And without proof, that feature is satisfied. And actual actual and forecast prediction. This is forecast error. Right? K-step ahead forecast. If you can calculate the variance of this one, and take the square root of that, and add it to 2 times standard deviation of forecast error, that is going to be your 2 standard deviation forecast error band, confidence band. So if you can calculate this one analytically, it's okay. You can calculate this conditional expectation to set this forecast, and also if you calculate standard deviation for this forecast error, then you can calculate 2 standard deviation band. That's analytical way, and very complicated. So when we see next time, we'll do it slightly differently. Do it using a procedure called bootstrapping. So we can generate forecast and upper bound and lower bound for stationary time series, as well as forecast, upper bound, and lower bound for non-stationary time series. Probably we need to spend for another week, so 2 lecture hours to complete this. Or if we speed up, it takes about 1 more lecture hour. But because these are basics of basics, so we try to spend some time so that we can follow this. So this is actually our first goal, to generate forecast and its uncertainty confidence band. So let me pause here. This is very weird. We did a lecture, but it says only 39 minutes. I wonder. System is frozen. Anyway, well, I'm done for this week.